Hi viewers, welcome to my class on mechanics of materials. In this class, I'll continue with the derivation of Euler's formula for a column with one end fixed and other end free. Let us consider the case of a column with one end fixed and other end free. It is firmly fixed at the one end and the other end is free. There is no support at the other end. And load is acting at the free end. Now as the load acts on the free end, the column buckles like this. So free end, there will be a movement. So it is not fixed in position or direction. One end is fixed in position. The position cannot change, and also rotation is prevented. So this end, fixed end, we can say one end is fixed in position and direction. So instead of one end fixed and other end free, we can also state that column is fixed in position and direction at one end and the other end is not fixed in position or direction. Now the differential equation for the deflected curve, you can write it as EI d square y by dx square is equal to bending moment. Bending moment you have to write. So it is EI d square y by dx square is bending moment. Let us consider a section at a distance x from the fixed end. Now lateral deflection is given by y. Now differential equation for the deflected curve is EI d square y by dx square is equal to bending moment. Now the bending moment at this section is P is producing a anti-clockwise moment at this section. So P into y, but it is minus. So minus Py plus M. So we get plus M minus Py. So at this section, the net moment of these all the forces on one side, this side I am taking the bottom portion. So net moment summation is plus M minus P into y, this distance, P into y minus Py, anti-clockwise, this is clockwise. So plus M minus Py, that is the net bending moment at this section. Now M you can replace. Now if you go for the moment summation for the whole structure, plus M and the moment due to these forces, because they are not now collinear, the column has deflected, the free end has moved. So between these two forces, they form a couple, and the lateral moment at the free end, we will put it as A. Then P into A is a counterclockwise moment acting on the column. Now the fixed end will produce a resisting moment. At the bottom, the fixed end, there is a resisting moment formed, and this resisting moment M minus P into A, that is a couple formed by these forces, minus P into A is equal to 0. That is a moment summation. M minus PA is equal to 0, or M is equal to PA. So the resisting moment should be equal to the moment produced by these forces, but in opposite direction, which is trying to balance the column. So this resisting moment is PA. So I am just replacing this M by PA. So PA minus PY. So we get EI d square y by dx square is equal to PA minus PY. Now minus PY I will take to the left hand side. So EI d square y by dx square plus PY is equal to PA. Now dividing by EI, you get d square y by dx square plus P by EIY is equal to P by EIA. Now I'll substitute M as root of P by EI. Root of P by EI as M, or P by EI is M square. So P by EI is replaced as M square. So here again it's M square. So d square y by dx square plus M square y is equal to M square A. Now the solution of this differential equation is given by y is equal to C1 cos mx plus C2 sin mx plus this constant A. and that A is the free end deflection. So this is a solution for the deflected curve. So y at any distance x is given by this expression. Now we will substitute the end conditions, non-boundary conditions. Now this equation you can differentiate. You will get dy by dx, or slope of the deflected curve. So if you differentiate this, you get dy by dx is minus c1 m sin mx, minus c1 m sin mx plus c2 m cos mx, plus this differentiation of this constant is 0. So I have differentiated that equation. Dy by dx is minus c1 m sin mx plus c2 m cos mx. Now we have the condition dy by dx slope is 0 at the fixed end. The slope of the deflected curve will be 0 at the fixed end, because the column cannot deflect here. It will remain straight at the fixed end, then start deflecting after some distance. So the initial part at x is equal to 0, dy by dx is 0. So when x is 0 means at the fixed end this column remains straight, the slope of the deflected curve will be 0. So when x is 0, dy by dx is 0. So putting this condition here in this differential equation, or in the equation of slope, x is 0, dy by dx is 0. When x is substituted as 0, sin 0 is 0, okay, cos 0 is 1. So 0 is equal to c1m into 0 plus c2m into 1, or you get c2m as 0, or c2m, m cannot be 0, so c2 is 0, because m is root of p by ei, that cannot be 0, so then load should be 0, so c2 has to be 0. So the solution of the differential equation reduces. The solution is this, okay, in that c2 is 0, you get y is equal to c1 cos mx plus a, y is equal to c1 cos mx plus a. So by substituting one boundary condition, the solution reduced to this form. Now we have one more constraint here at this fixed end. When x is 0, y is 0. There is no deflection also at the fixed end. So it's fixed end, deflection and slope is 0. So x is 0, deflection is also 0. Putting x as 0, cos 0 is 1, y is also 0. So c1 into 1 plus a is equal to 0. c1 in plus a is equal to 0, or c1 is minus a. So you are getting the constant c1 as minus a. So putting that c1 as minus a, your equation reduces to y is equal to minus a cos mx plus a. Y is equal to minus a cos mx plus a. Solution is y is equal to minus a cos mx plus a. Now to solve for m, we know one more condition, when x is equal to L and y is equal to a. That means when x is equal to L at the free end, the deflection is given by a. So when x is equal to L, deflection is a. You can substitute that condition in this solution. X is equal to L, y is equal to a. Substitute that condition in the solution. A is equal to minus a cos ml plus a. A is equal to minus a cos ml plus a, or cos ml. So a, if you take to the left hand side, you will get a minus a 0. So a cos ml has to be 0. A cannot be 0, because a is also 0 means there is no deflection. A 0 means no deflection. So cos ml has to be 0. Cos ml to be 0, the solution for ml is pi by 2. When cos pi by 2 is 0, cos 3 pi by 2 is 0, cos 5 pi by 2 is 0. So out of this you have to take the least value of the solution, so that the column at the least load columns buckles. So we need not take higher values because we have to find out the least load at which the column buckles. So taking that minimum value, ml is equal to pi by 2 and m is root of p by ei, l is equal to pi by 2. Now squaring it, p by ei l square is equal to pi square by 4, or p you can find as pi square ei by 4l square, or 4l square you can write it as 2l whole square. So P is equal to the Euler's crippling load or buckling load is pi square ei by 2l whole square. This is for a column with one end fixed and other end free. That's all for today. Thank you for watching.